Hi everyone, it's Rob Thompson, Sales Manager here at SYS Systems. I'm joined with Matt Jones, Senior Application Engineer from Stratasys, and today we're going to talk a little bit more about the FDM process from Stratasys and the FDM technology. So I don't know if you want to kick us off, Matt, and just give us a bit of a brief in terms of what FDM is and what it means to people.
Will do. So FDM, Fused Deposition Modelling, was invented well over 30 years ago by Scott Crump in his kitchen as a project, I believe, for his daughter. I always describe it as akin to a glorified glue gun. So you're basically taking real engineering grade thermoplastics, melting it, and as it extrudes, you're plotting it in an XY and building it up in Z. So it's a pretty straightforward process compared to other technologies out there in the additive manufacturing in the world. But it allows you to do real engineering grade thermoplastics, so ABS, ASA, nylon 6, nylon 12, and filled materials, along with some more exotic materials as well.
FDM as a process, then, a lot of people have seen, because I've seen out there's hundreds of different FDM manufacturers of machines, and they'll start from a few £100 and go up into the hundreds of thousands of pounds. So I suppose from a consumer's point of view, and it could be quite confusing to see where you fit within FDM technology. Yeah. Where does Stratasys fit with FDM?
So you're right, it's definitely a bit of a minefield. So you've got FDM, obviously Stratasys invented that, and as the patents have expired over the years, that's allowed other people to come into play. So you've got the Fused, the FFF sort of range of systems that are out there. Stratasys really comes into play when you want high production, repeatable parts. So the coefficients of variance is in the high 90%, which means basically you know that when you're going to press play on a machine and print a part, it's going to come out time and time again, but also repeatably with mechanical performance of the parts that you're doing and the accuracy of the parts as well. So really, whether it's for prototyping or end use, you want to make sure you've got consistency within the products you're developing, whether it's for prototypes or for end use or for tooling, whatever it is. And you don't get that with other systems that are open to the air or don't have the temperature controls that we have, or don't have the same sort of controls on the XY and on the heads and the extrusion rates and things like that.
Oh, that's brilliant. So yeah, I think that's what we hear a lot of when people tend to go in for the entry-level style machines. It can certainly prove to people that they would require a 3D printer, and it gives them some advantages in terms of getting parts on the desk and start to trial things. But as you say, the reliability, repeatability of the Stratasys technology across the full range of machines that we've got is really second to none, isn't it?
Yeah, you can't discount sort of low-end systems to start off with, because you've got to dip your toe in the water and have a play. And as you said, it's a larger investment with the Stratasys equipment because of the quality of it, but it's also the speed as well. So something that takes 5 hours on our system could take 12 hours on another system, or even longer depending on which one it is. So it's really important. If you want something quicker, you want repeatable accuracy, quality, surface, mechanical performance, then I'd like to think that Stratasys was the way to go forward.
That's it. I think people sometimes don't probably count on the failure rate of these technologies as well sometimes, and as you say, it only takes a couple of failures for one of those machines for then the return on investment for a more expensive, more industrial, professional bit of kit to really pay off for people, because ultimately they've got their customers to satisfy in terms of getting parts and getting down the line with their manufacturing process as well, I suppose.
Yeah, exactly. And it also, like, if you had a system on a manufacturing floor to support, whether it's a dry goods, manufacturing site where they're packaging components and things like that, if something broke on the shop floor, that packaging line is going to go down, for example, and then you've got to print something if you didn't have the spare part in stock. So being able to print on demand when you want what you want, and quickly, repeatably, and reliable is a key thing. It's a massive selling point as well.
So where would you see at the moment, obviously we know that really FDM as a process, as it was invented years ago, really I suppose starts out as a prototype in technology for most people in the early stages. That's kind of evolved a long way past that now, hasn't it? So where do you see FDM really being utilised now in terms of applications as a technology?
It's a good question, because the material that we offer allow you to have a huge diversity of applications. It can be absolutely anywhere, to end use parts inside a car, on a train, on a plane. Military and defence is a big one as well, whether it's for parts for your shoes. It literally can be anything. The more the materials progress, then obviously, as I said earlier, it allows us to go into different markets as well as so for end-use parts, for example, although this is an FDM part, you can metallize it, you can paint it, you can spray it up. So a lot of people think, well, FDM doesn't have the best surface quality in the world. We're going to look at DLP, although we do offer that as well as. But you can get a very high surface finish. You can seal them as well. FDM is inherently hydroscopic, so it absorbs moisture and is porous. Anyway, so for subsea applications, it's not a problem. You can seal them as well. It just depends on what you need from a material point of view. For me, as an engineer, the material's the starting point, because that points me to the right technology. So as an application engineer, when we support you and other resellers out there, that it's a case that we want to be able to say, look, this is what we want, or the customer wants, this is the requirements from them, and that leads us down the map, the portfolio of products we have, quantities, quality, accuracy that you need from it.
Yeah, there's always a range of questions, isn't there, when you're looking at these applications. I think what's interesting that I've found in the last few years is that more people are not necessarily trying to tackle the holy grail of end-use parts, but they're actually looking at where can I use this technology in the manufacturing process as well. And you've really come with quite a few nice examples which you might want to cover in terms of where the printed part has helped aid in the manufacturing process, as in tooling. Have you got some examples that you want to talk about with that?
So give you an example. So this is Ultem 1010 as a material. So it's used as a composite layup tool. So here we're able to print the part. You can seal it if you want to, or you can cover it with a film. And basically you're going to put your plies on top, consolidate and cure it in an autoclave. But carbon fibre tooling, whether it's sacrificial tools, mandrels, whatever, is a huge part. So again, automotive, it could be for sports. So we've got a lovely case study on the luge bobsled team from the US for racing on yachts and things as well. It doesn't have to be carbon fibre, it could be glass fibre. So ASA is a really good material for sort of room cure pre-pregs as well as. So also press tooling, again off the 370 CR here is an example. So it's the nylon carbon fibre filled material, and you can literally get hundreds and hundreds of stamps off this. So if it's a different shape, we've got a guide as well that you can follow on how to process the files and the types of shapes that we can do, but literally hundreds and hundreds, and within the norms of normal manufacturing processes, the tolerances and the accuracies as well.
Fantastic. It's got the wear resistance that you'd expect from a tool.
Yeah, the coefficients of friction for this material is extremely good, really good surface quality as well. So yeah, spot on, really good for the application.
That's brilliant. And a little bit more perhaps about the engineering side of things, because that's a market that we've seen in the last couple of years really take off. Maybe on the shop floor we'd not really seen 3D printers predominantly, but things like soft jaws, perhaps a little bit more about that.
Soft jaws, as an example, we have one ready to hand. So again, depends on the materials that you want and how you're going to clamp it up and the forces and the direction of the forces. But to hold an object in place during a CNC process, FDM is an ideal solution because the materials are very, very strong and very robust. So it's not a case of printing it once and throwing it away once you've done the iteration or the tooling on the machining on the system. You can use it time and time and time again, and there's loads of case studies from us out there that you can follow. Again, don't worry about moisture absorption, chemicals, oils, all that sort of stuff. The materials are resistant to those, so it's perfect for it. And the way that works is you'll take the actual shape of the part, bring it into CAD, and then we'll take it as a net shape right around the part, so it holds it and cradles it really nice and snug. Trying to free up the time of the CNC, because you have to obviously machine the fixtures to hold it in place anyway, so you're freeing up more time by printing it on an FDM system.
Yeah, there's so many benefits to the engineering workshops really, in terms of quality control, even printing a physical part, taking it down the process, writing your programs, so you're looking at any collision detection, and then even passing that through to the quality control guys to write a program for the CMM, and maybe even printing a fixture to hold it within the CMM. So we're seeing a lot of uptake really within that market. End of arm tooling, perhaps that's another maybe area to have a chat about.
End of arm tooling again. So traditionally, most of it's metal. We'll dabble in other sort of plastics, machine plastics. But again, with the filled materials, you're able to have the strength and stiffness, but also, you don't get the torsion, the twist that you get from some other materials that are out there. So they are lightweight, for one. So there are different examples. If you just pass me those over. Try and do two things at once. So you don't have to print a model completely solid. So you can do it sparse double dense. You can even vary the infill that you want, and also change the raster angles to the way that we lay the material down inside as well. So if you want a little bit more stiffness in one area, you can do it solid. If you want to lightweight in another area, you can do that sparse. So if it's an end of arm tool for a robot, for example, it gives you the flexibility, I guess, to save on the preventative maintenance side, because you're not putting it under excessive stress. But again, lots of examples out there where we've put the air lines inside. You've got the vacuum suction cups on the top as well. So really good, whether it's for sucking and holding packages, whether it's for laser cutting or for water jet cutting as well. So again,
yeah, there's such a wide breadth of applications, as you say. I mean, down the years of you being in the industry so long, you see so many different things, and unfortunately, quite a few things you're not allowed to talk about, I suppose.
Yeah,
what's sort of next for FDM? I mean, is it material development? Do you think is probably the area?
Yeah. So the newer materials, or what we're thinking about, we do studies every year. We reach out to the existing customer install base and to you guys as well, to find out where you think and what customers want from us. So whether it's newer field materials or new requirements for fire retardancy, or higher coefficients of friction, so better wear rates on the materials, whether it's materials for subsea applications, defence applications, the list is endless. I can't say too many things, otherwise I'll get shot. So,
so in terms of key materials then, we've talked a bit about the applications. What would you say, I mean, I know we've got various materials that could be used in different levels, biocompatible, things like that, but in terms of the here and now, what would you say is the key sort of materials that you see being utilised at the moment?
So the big adoptions is obviously the Ultem 9085, so that's the FST certified material. So whether, again, rail, aerospace, it doesn't matter. If you need a material that is FST compliant, so flame, smoke and toxicity, you can have that. That's one of the preferred materials. Part of the OML gives you the validated ones as well, so you can have it in white, you can have it in red, Jana white, aircraft grey. There's other material colours as well available for it again. So it's a big adoption. TPU from the F123 series, again, the surface quality that you get off elastomeric based material is really important. It's a very tricky material to print. This is a big adoption as well. Again, whether that's for protective covers, for NOx dampings, or for hosing housings and things like that, it's a good idea. Nylon 12 CF. So it's got 35% carbon fibre on the inside, exceptionally strong and stiff. You don't get the twist or the torsion inside the part. Again, loads of applications for it, so those work really well. ASA, ABS, the usual ones for prototyping, mock-ups and things like that work really well. As well as
with nylon 12 CF, just to sort of touch on that particular material, that seems to be a really sort of popular 3D printing material at the moment. People are looking for carbon fibre filled materials. We get asked about it all the time. Why is our carbon fibre nylon 12 quite a unique proposition, and why do we sort of sit at the top of the tree there?
So it's the weight of the carbon fibre inside, and it's also the matrix that we've got with regards to the nylon material that we use, then coupled together with the build heated chamber, the way that we extrude the materials with the print heads, and all the software in the background for the rasters, and the way that we do the tool parts. It all ends up giving us a really high surface quality and very mechanically strong parts.
Yeah, I think that's one of the things that we've seen, when we've done a lot of testing against various different other nylon 12, nylon-based carbon fibre materials from people. It really is a case that having the 35% chopped carbon fibre through the entire part really sets you apart on the overall strength of the component, doesn't it? So that was a little bit more about our FDM technology. As I say, we're going to be covering across some of our different technologies as well, so please do stick with us and enjoy the videos.